Our universe is a vast and wondrous place filled with countless stars, galaxies, and planets. Yet among all these marvels, black holes stand out. They're regions where the laws of nature seem to break down completely. Imagine a massive star collapsing under its own gravity, crushing matter into an incredibly tiny point with almost infinite gravitational pull. Nothing, not even light, can escape. They are the universe's ultimate predators, lurking in the darkness of space. Black holes remain stubbornly out of reach, invisible by their very nature. We can only infer their presence by observing their effects on the things around them. The idea of a black hole isn't new, but then Albert Einstein changed everything with his theory of general relativity. Instead, it's a curvature of space-time itself. Black holes are an extreme example of this. A black hole's immense gravity pulls in surrounding gas and dust, forming a swirling disk. As the material gets closer, it heats up, glowing brightly in X-rays. This is how we first detected black holes. The abyss was real. So we know that black holes exist. We know how they form. We can even observe their powerful influence on the cosmos around them. But there's one fundamental question that continues to puzzle scientists and, honestly, capture the imagination of us all. It's the question that lies at the very heart of this deep dive. What is actually inside a black hole? What happens when you cross that point of no return, the event horizon? What secrets lie hidden beyond that dark, impenetrable veil? This is one of the biggest unanswered questions in all of science today. The event horizon is the boundary of the black hole. It's not a physical surface you could touch. It's simply the point in space where the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. Once you cross it, your fate is sealed. The laws of physics as we understand them predict that you'll be pulled inexorably towards the center. All the matter that has ever fallen into the black hole is crushed into an infinitely small, infinitely dense point. This point is called a singularity. It's a place where space and time cease to have any meaning. But is a singularity really what's at the center? Our current theories, general relativity and quantum mechanics, are our two best descriptions of the universe. General relativity describes the world of the very large, like stars and galaxies. Quantum mechanics describes the world of the very small, like atoms and particles. The problem is, these two theories just don't agree. Inside a black hole, you have an immense amount of mass packed into a tiny space. It's a place where both theories must apply, but they give us different, contradictory answers. This conflict tells us our understanding is incomplete. This is why the question of what's inside a black hole is so important. It's not just about satisfying our curiosity. It's about finding a new, more complete theory of physics, a theory that can unite gravity with the quantum world, a theory of everything. Solving the mystery of the black hole's interior could unlock the next great revolution in our understanding of the universe. It could reveal new dimensions, new particles, or even tell us that our universe is just one of many in a vast multiverse. The journey to the heart of a black hole is a journey to the very edge of human knowledge. To understand black holes, we journey back to witness the death of a colossal star. Imagine a star 20 times more massive than our sun, burning for millions of years. Eventually, it runs out of fuel. The core collapses catastrophically, triggering a supernova. If the star is massive enough, gravity crushes the core into an unbelievably small, dense point. A black hole is born. It's gravity's ultimate triumph. Supermassive black holes lurk at the heart of most large galaxies. So, what are the key features of these cosmic titans? Let's dissect the anatomy of a black hole. Contrary to their name, they are not empty holes, but regions of space-time, containing an incredible amount of matter crushed into an impossibly small area. The most famous feature is the event horizon, the point of no return. At the very heart lies the singularity, the ultimate destination for anything that crosses the event horizon. Surrounding the black hole, you will often find a swirling, glowing accretion disk. Finally, for some rotating black holes, there's the ergosphere, where space-time itself is dragged around by the black hole's spin. Black holes are active, powerful cosmic engines. Their immense gravity makes them the ultimate predators, shaping their environments. Any object that wanders too close is caught in its grip and stretched. This process, nicknamed spaghettification, is a dramatic display of a black hole's power. The remains join the swirling accretion disk. Intense heat and magnetic fields create relativistic jets. These powerful jets of particles are blasted out at nearly the speed of light. Supermassive black holes at galaxy centers act as cosmic anchors. Their gravity helps hold the galaxy together. Black holes are cosmic sculptors and regulators, playing a vital role in galaxy evolution. Beyond their scientific importance, black holes have captured our collective imagination like few other concepts in the universe. They are a cornerstone of science fiction, an ultimate symbol of the unknown. This potent mix of terror and wonder makes them the perfect device for storytelling. They can be a terrifying monster, a gateway to another dimension, or a shortcut across the galaxy. Their mystery is a blank canvas for our greatest hopes and deepest fears about the cosmos. They are often depicted as cosmic whirlpools or wormholes, offering a perilous path to distant worlds. The possibility of a gateway through space-time is a powerful and enduring myth. This is science that sounds like magic. As long as that question remains unanswered, black holes will continue to be the ultimate icon of science fiction. Let's journey to a black hole. From a safe distance, it appears as a perfect circle of blackness against distant stars. Light bends around its edge, creating a mesmerizing halo. This boundary is the event horizon, a one-way door. Approaching it, time itself warps, a prediction of Einstein's relativity. Gravity warps time. The stronger the gravity, the slower time flows. Near a black hole, time slows dramatically. Approaching the event horizon, we travel into the universe's future. As we descend, gravity dominates. Tidal forces become monstrously powerful. Imagine falling feet first. The difference in gravity would stretch you, a process called spaghettification. Stars aren't immune. Supermassive black holes tear them apart. But for supermassive black holes, tidal forces at the event horizon could be gentle. You could cross the event horizon completely intact without even realizing it. Let's approach a supermassive black hole. We are now at the very edge of the event horizon. What do we see? The event horizon is a mathematical boundary defined by gravity. It's the ultimate one-way street, and then we cross. Our fate is sealed. We have now passed the point of no return. From this moment on, our destiny is singular and unavoidable, leading to the center of the black hole. Now we are inside the black hole. We have crossed the event horizon. The connection to the universe we knew is severed forever. As we are pulled deeper, the tidal forces would now begin to grow exponentially. The spaghettification process would begin in earnest. The very atoms that make us up would be torn apart. Because of the extreme warping of space-time, the singularity would appear to be in every direction at once. Our final moments would be a chaotic, violent plunge into a region where space and time cease to have any meaning. It would be a journey into the heart of a cosmic mystery, a place from which no information can ever return. This clash is where the real mystery begins, and where we must look for new ideas to understand what truly lies at the heart of darkness. We have reached the limit of our understanding, ending at the singularity. It is a point of infinite density and zero volume where equations break down. To venture further, we need quantum mechanics. It seems incompatible with general relativity. The singularity is the ultimate battleground where these two titans of physics must meet. To truly understand what happens, we need a theory of quantum gravity. Finding this theory of everything is the holy grail. This quantum fuzziness might be what saves us from the absurdity of infinity. It suggests the singularity may not be a point at all, but something far stranger. For decades, the event horizon was seen as a one-way door. Anything crossing it was lost forever, violating quantum mechanics' rule that information can't be destroyed. This contradiction, the black hole information paradox, stumped physicists. In 1974, Stephen Hawking changed everything. By applying quantum mechanics near the event horizon, he discovered black holes emit faint radiation. Now called Hawking radiation, this meant black holes slowly lose mass and could eventually evaporate. The process: virtual particle pairs pop into existence at the event horizon. One falls in, the other escapes as real radiation. The escaping particle draws energy from the black hole's mass, causing it to shrink. Over unimaginable timescales, even the largest black holes could vanish in a final flash. Hawking's insight offered hope. Maybe information isn't lost, but somehow encoded in this faint radiation. The paradox wasn't solved, but the rules of physics were forever changed. Hawking's discovery was groundbreaking, but it deepened the mystery. If black holes evaporate, does the information inside vanish too? Hawking's math suggested the radiation was random, no information escapes. This clashed with quantum mechanics, which insists information must survive. The paradox pits quantum theory against Einstein's relativity. One must give. Enter string theory. It imagines black holes as fuzzballs of vibrating strings, not singularities. In this view, information isn't destroyed, but tangled in the fuzzball's structure. Hawking radiation, then, could carry information out, not just random heat. Over time, the black hole radiates away, releasing its secrets. It's an elegant idea, but still unproven, a bold step towards resolving the paradox. The quest for a deeper theory continues. The mysteries inside black holes have inspired wild ideas. 1. The singularity could be a gateway, birthing a new universe, a cosmic tree with each black hole as a branch. Our universe might have sprung from a black hole in another cosmos. Another theory, loop quantum gravity, says space-time is woven from quantum loops, no true singularity. Matter collapses to a Planck star, then rebounds, hidden inside the event horizon. This bounce could create a white hole, the opposite of a black hole. Matter escapes, nothing enters. These ideas are speculative, but they offer new ways to think about creation and the fate of information. Black holes may not be the end, but a beginning. The truth remains hidden, waiting for a breakthrough. Just as physicists made progress, the Firewall Paradox erupted in 2012. It asks, can information escape a black hole without breaking the laws of physics? Quantum mechanics says information must get out. Relativity says crossing the event horizon should feel uneventful. But quantum rules say a particle can't be entangled with two things at once. To resolve this, some proposed a firewall, a searing wall of energy at the event horizon. Any astronaut crossing would be incinerated, shattering Einstein's predictions. The paradox forces a choice: lose information or accept a deadly firewall. Neither is satisfying, highlighting the clash between our best theories. Some suggest space-time itself is built from quantum entanglement. The Firewall Paradox is a clue pointing toward new physics. Why can't we know what's inside a black hole? Because nothing, not even light, escapes. Light is our main tool for exploring the universe, but black holes trap it all. No telescope, no matter how advanced, can see past the event horizon. We're left to gather clues from the outside. The orbits of nearby stars, the glow of accretion disks, and gravitational waves from black hole mergers. These tell us about the exterior, not the interior, so we rely on theory, relativity, and quantum mechanics to imagine what's inside. But these theories clash in extreme conditions, leaving us with speculation. Without direct observation, we're piecing together a cosmic puzzle with missing pieces. The true nature of a black hole's heart remains one of science's greatest mysteries. For now, we can only guess what lies beyond the veil. Another barrier is causality, the rule that causes precede effects. The event horizon is a one-way boundary once crossed. Nothing can return or send signals out. The black hole's interior becomes a sealed pocket of space-time cut off from the universe. Even the best probe would be trapped, its data lost forever. This wall of causality means we can theorize endlessly about singularities, fuzzballs, Planck stars, or baby universes, but never test our ideas directly. Science thrives on experiment, but here we are locked out by the laws of nature. The event horizon is a cosmic point of no return both for matter and for knowledge. We're left to speculate, building models and debating possibilities. The answers may exist, but they're hidden behind an unbreakable wall. Black holes challenge the very limits of what science can know. With direct observation off the table, physicists have had to get creative. This has pushed theoretical physics to its most speculative and mind-bending frontiers. Freed from the immediate constraints of experimental verification, scientists can explore ideas that challenge our most basic assumptions about reality. One such wild idea is the holographic principle. This suggests that our three-dimensional universe might be just a projection, a hologram, of information stored on a two-dimensional surface at the edge of the cosmos. It's a bit like watching a three-dimensional movie that is projected from a two-dimensional film. The holographic principle was born directly from studying the physics of black holes. Scientists found that the amount of information a black hole can contain is not proportional to its three-dimensional volume, but to the two-dimensional area of its event horizon. This was a shocking discovery. It suggested that all the information about the three-dimensional interior is somehow encoded on its two-dimensional boundary. If this is true for black holes, could it be true for the universe as a whole? It's a radical thought that suggests space-time itself is not fundamental, but an emergent property of something deeper, a network of quantum information. Another set of wild ideas comes from trying to imagine reality without a singularity. We've talked about Planck stars from loop quantum gravity, where matter rebounds. Some physicists have taken this further, proposing that black holes could be portals to other places in our own universe. This is the concept of a wormhole or an Einstein-Rosen bridge. In this scenario, the black hole's entrance is connected to a white hole's exit somewhere else. You would fall into the black hole and, instead of being crushed, you would be shot out of the white hole into a different region of space or a different point in time. While wormholes are a staple of science fiction, they are incredibly unstable according to general relativity. Any attempt to traverse one would cause it to collapse instantly. However, some theories suggest that a sufficiently advanced civilization could potentially stabilize a wormhole using something called exotic matter, a hypothetical substance with negative mass or energy. We have never observed exotic matter, and it may not exist. But in the realm of pure theory, where we are trying to understand the absolute limits of possibility, these ideas serve as important thought experiments, pushing the boundaries of what the laws of physics might allow. A new window on the universe has opened up: gravitational waves. These ripples in space-time, created by violent cosmic events, were first detected in 2015. We can now listen to the universe. By analyzing gravitational waves from black hole mergers, we can measure their masses and spins. The ringdown is our best hope for probing the event horizon. If the signal deviates from Einstein's predictions, it could be evidence for new physics. Our detectors are becoming more sensitive. These observatories are our best bet for finding cracks in our understanding. We have traveled to the very edge of knowledge and peered into the abyss. Our exploration has taken us from the fiery death of stars to the theoretical heart of a singularity. We've seen that black holes are fundamental architects of the cosmos, shaping galaxies and challenging our deepest theories. They are the ultimate laboratory for extreme physics. Black holes are defined by the questions they pose, not the answers they provide. What truly lies beyond the event horizon? The black hole stands as a monument to our own ignorance, daring us to find a new theory. When we stare into its darkness, we are also looking at the limits of our own understanding. Pointing the way towards the next great leap in our cosmic comprehension, the enigma endures, and so does our quest to solve it. Let's take a moment to look back at the path we have traveled. We began by witnessing the birth of a monster, understanding how the gravitational collapse of a massive star can create an object so dense that not even light can escape. We dissected its anatomy from the swirling superheated accretion disk to the point of no return event horizon and the theoretical singularity at its heart. We saw how these cosmic predators are not just passive objects, but active engines that shape their environments, anchoring galaxies and regulating star formation through their immense gravitational influence and powerful jets. Our journey then took a more perilous turn as we imagined a trip into a black hole. We explored the bizarre effects of extreme gravity, from the dramatic slowing of time known as gravitational time dilation, to the gruesome process of spaghettification. We crossed the invisible threshold of the event horizon, the point where escape becomes impossible, and all future paths lead only inwards. We contemplated the final moments of this journey, a descent into a region where space and time swap roles, and where all matter is destined for a central point where the laws of physics as we know them cease to function. From the ashes of this classical picture, we explored the quantum quandaries that arise. We delved into Stephen Hawking's revolutionary discovery of Hawking radiation, the idea that black holes are not completely black, but slowly evaporate over eons. This led us to the profound information paradox, the deep conflict between general relativity and quantum mechanics over whether information can be destroyed. This single puzzle has driven physicists for decades, leading to radical new ideas like string theory's fuzzballs and the mind-bending notion that the universe could be a hologram. Finally, we confronted the immense challenges that prevent us from finding definitive answers. We are limited by the Wall of Causality, unable to send a probe inside and get a report back. We're staring at a locked room. This has pushed scientists to the wild frontiers of theory, exploring concepts like baby universes and traversable wormholes. Yet we also found a glimmer of hope in a new kind of telescope, gravitational wave observatories, which allow us to listen to the ringing of space-time itself, potentially revealing the first clues about the true nature of the event horizon and what lies beyond. The story of the black hole is far from over. We are living in a golden age of black hole research. Our tools are becoming more powerful. The Event Horizon Telescope has given us our first ever direct image of a black hole's shadow. These images are just the beginning, allowing us to test Einstein's theories. At the same time, our gravitational wave detectors are being constantly upgraded. They're becoming more sensitive, allowing them to detect faint whispers of space-time ripples. Thousands of physicists are working on the problem of quantum gravity. The intense debate and collaboration happening today will drive the next great scientific revolution. What discoveries await us? The pursuit is well underway. The quest to understand black holes is pushing the boundaries further than ever before. In the end, our fascination with black holes comes down to a fundamental human trait, our sense of wonder. We are a curious species. We look up at the night sky and we don't just see points of light. We see other suns, other worlds, and other possibilities. We ask questions. What are they? How did they get there? And what is our place amongst them? The black hole represents the ultimate expression of this cosmic curiosity. It is the biggest, most profound question mark that the universe has hung in the sky for us to ponder, a symbol of the vastness of our ignorance. This sense of wonder is the engine of science. It's what drove Einstein to rethink the nature of gravity, and what drove Hawking to question the permanence of a black hole. It's what inspires a new generation of scientists to build bigger telescopes, to write more complex code, and to dream up new theories about the universe. The pursuit of knowledge is not just about finding practical applications or technologies. It's about satisfying a deep, innate need to understand the world around us and the fundamental laws that govern our existence, no matter how strange or counterintuitive they may be. So the next time you look up at the star-dusted sky, take a moment to think about what you cannot see. Think about the silent, invisible giants lurking in the darkness between the stars. Think about the supermassive behemoth at the heart of our own galaxy, around which our sun and billions of other stars are dutifully orbiting. These objects are not just distant astronomical curiosities. They are an integral part of our cosmic story, a story that is still being written. They are a profound reminder that there are still great mysteries left to solve. The journey to understand what is inside a black hole is, in many ways, a journey to understand ourselves and the limits of our own minds. It teaches us humility in the face of the vast cosmos, but it also fills us with hope and excitement for the discoveries that are yet to come. The universe does not give up its secrets easily, but the quest to uncover them is one of the noblest and most thrilling adventures we can undertake. The darkness holds the key, and our journey into it has only just begun. Thank you for joining me on this deep dive.